Hello students, welcome back to chapter 9, Force and Laws of Motion. In the previous videos, we have learned Newton's first two laws of motion. The first law of motion tells us how an applied force changes the motion, and the second law provides us with a method of determining the force. The third law of motion states that when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. For example, suppose there are two objects, A and B. If the object A exerts a force on the object B, the object B also exerts a force on the object A. These two forces are always equal in magnitude but opposite in direction. And these forces act on different objects and never on the same object. For example, in the game of football, sometimes we, while looking at the football and trying to kick it with a greater force, collide with a player of the opposite team. Both feel hurt because each applies a force to the other. In other words, there is a pair of forces and not just a single force. Here the two opposing forces are known as action force and reaction force. Thus, Newton's third law of motion can be stated like this. To every action, there is an equal and opposite reaction, and they act on two different bodies. When one body exerts a force, that is the action force, on another body, the second body also exerts a force which is a reaction on the first. These forces are always equal in magnitude but opposite in direction. And it's very much important to note that even though the action and reaction forces are always equal in magnitude, these forces may not produce accelerations of equal magnitudes. That is, even though the forces are always equal, but the acceleration produced, they are not the same, it's not equal. The reason is that each force acts on different objects, and this different object, they may have different masses. That's why the acceleration is different. When a gun is fired, it exerts a forward force on the bullet, and the bullet exerts an equal and opposite reaction force on the gun, and this results in the recoil of the gun. And the gun has a much greater mass than the bullet. So the acceleration of the gun is much less than the acceleration of the bullet. The third law of motion can also be illustrated when a sailor jumps out of a rowing boat. As the sailor jumps forward, in the picture you can see, when he jumps forward, the force on the boat moves it backwards. So these are some of the examples of Newton's third law of motion. We can see some more activities of the applications of Newton's third law of motion. Here in the picture you see a book, that is A, is kept on a table. The book exerts a force in the downward direction. The table, that is B, it also exerts a force on the book, but the force exerted by the table is in the upward direction. Here, the forces exerted by the book and the table, that's the action force and reaction force, they are in opposite direction but in equal magnitude. As these two forces, which are equal in magnitude and opposite in direction, they act on two different objects, so they do not cancel each other. Another example you see, a person, when he walks on the ground, his foot pushes against the ground backwards. That is, the action force and the ground in turn exerts a force on the foot, which is the reaction force pushing the foot forward. Here, this is the force which is exerted by the ground on the foot, which is in the opposite direction, that helps us to move. Third law of motion can be used to explain rocket propulsion and the recoiling of the gun that we have seen. You know, birds, while flying, they push the air downwards with the help of their wings, which is the action force, and the air in turn exerts a force on the bird in the upward direction, which is the reaction force. Next, we are going to see what is conservation of momentum and law of conservation of momentum. In physics, this conservation means no change. Then what is conservation of momentum then? No change in the momentum. See here, there are two objects, A and B is shown in the picture. A and B, that is two balls. Suppose A and B be two balls of mass MA and MB, moving in the same direction along a straight line at different velocities UA and UB respectively. That means the mass of the object A is MA, that of the ball B it is MB, and the velocity of object A, UA, and UB is the initial velocity of the ball B. There are no other external unbalanced force acting on it. We are not exerting any force on the two balls. Let the velocity of the ball A greater than the velocity of the ball B, and the two balls collide with each other for a time t. When they collide with each other, the ball A exerts a force F of AB on the ball B, and the ball B exerts a force FBA on the ball A, and that is shown in the second part of the figure. That is the collision of the two balls A and B. After collision, the object A and B, they move with velocities VA and VB respectively. VA is the final velocity of the object A and VB that of B. Now, we can find out the momentum of the objects A and B before collision and after collision. Before collision, momentum of the ball A, that's equal to mass of A into initial velocity of A, that is MA multiplied by UA. Same way, momentum of the object B before collision, mass of B multiplied by initial velocity of B, that is MB multiplied by UB. From this we can find out the total momentum of the balls A and B before collision. Total momentum of A and B before collision is equal to MA UA plus MB UB. This is the total momentum before collision. Now let us find out the total momentum after collision. After collision, momentum of the ball A, that is MA VA. Because after collision only the velocity changes, mass remains the same. That's why MA VA. Then momentum of the ball B, MB VB. So total momentum of A and B is equal to MA VA plus MB VB. Is that clear? Now we got the total momentum of balls A and B before collision and total momentum after collision. Now we can see what is the change in momentum of the object A. Change in momentum, you know that final momentum minus initial momentum. Change in momentum of A means final momentum of A minus initial momentum of A. That is MA VA minus MA UA. Here mass is common, and therefore rate of change of momentum of the ball A. Rate of change of momentum means change in momentum upon time. Divide it with T. So we get MA as it is common, take it as a common factor, and MA into VA minus UA upon T. Same way we can find out the change in momentum of the ball B, that is mb vb minus mb ub. Therefore, rate of change in momentum of the ball B, that is mb into vb minus ub upon t. According to Newton's third law of motion, we know that this action and reaction, they are equal in magnitude but opposite in direction. As it is opposite in direction, we can show it with the help of a negative sign. So we can write f of AB is equal to minus f of BA. And in second law of motion, we have seen that rate of change of momentum is equal to the force. So we can equate it ma into Va minus Ua upon T is equal to minus Mb into Vb minus Ub upon T. T and T, that is the denominators common on LHS and RHS. We can cancel it. Then we will get MAVA minus MAUA is equal to minus MBVB plus MBUB. Why it's plus there? Minus into minus becomes plus. So we can write MAUA plus MBUB is equal to MAVA plus MBVB. That means, see the left hand side, that is the total momentum before collision that we have already calculated. Right hand side is the total momentum after collision. So it is proved, it is shown that total momentum of two objects before collision is always equal to its total momentum after collision. So we can state law of conservation of momentum like this. The sum of momenta of two objects before collision is equal to the sum of momenta after collision, provided there is no external unbalanced force acting on them. This is the statement of law of conservation of momentum. So you have to practice the derivation by writing. So the question can be like this: state and prove law of conservation of momentum. So I hope the topic is clear to you, and the numericals will be solved in the next video. So read the textbook thoroughly. Thank you.